How did Vikings' raised stone foundations keep their houses from rotting for 200 years? The year is 1000 CE. Rain hammers wooden longhouses across Scandinavia as winter approaches. Timber walls sit vulnerable to moisture, frost, and decay that could destroy a home in decades. Here's the main point. Vikings prevented their wooden houses from rotting by building them on raised stone foundations that lifted timber completely off damp ground. Archaeological evidence from 8 major Norse settlement sites proves these stone foundations raised sill beams 30 to 50 centimeters above soil level. No direct ground contact, no capillary moisture wicking upward, no fungal decay eating through support beams. Tonight we build 2 identical timber structures, one using the Viking method with raised stones, one sitting directly on earth, and expose them to a full winter cycle. The moisture sensors will tell the truth about which method keeps wood driest. The thermal cameras will reveal which foundation stays warmer. But there's a hidden technique Vikings used that modern science only recently validated. A simple membrane trick that made their stone foundations even more effective. We'll test the numbers, measure the moisture levels, and prove which approach delivers timber that lasts centuries instead of decades. Could this forgotten Norse engineering method teach us something we desperately need to remember when building for the long haul? If this Viking investigation opened your eyes to what Norse builders accomplished with stone and timber alone, make sure to subscribe. We're uncovering more documented survival techniques that put modern convenience to shame. Comment your city and local time. We want to know where these Viking documentaries reach. The rotted timber post sits in my hands like a warning from the past. What was once a sturdy oak beam now crumbles at the touch, its grain eaten hollow by decades of moisture and fungal decay. This is what happens when wood meets wet ground, and it's exactly the problem Vikings solved over 1,000 years ago. Vikings kept their wooden houses from rotting by building them on raised stone foundations so the timber never touched damp ground, a simple solution that extended building life from decades to centuries. The physics of timber decay begins the moment wood contacts soil. Ground moisture moves upward through capillary action, the same force that draws water up a paper towel. Even in winter, soil holds 70 to 90% relative humidity, while frozen ground creates condensation when it meets warmer timber above. Dr. Sarah Patel, our structural engineer, explains the process with clinical precision. Wood is hygroscopic, meaning it absorbs and releases moisture from its surroundings. When timber sits directly on earth, it equilibrates to the soil's moisture content, typically 18 to 25% by weight. Above 15%, fungi thrive and decay accelerates, exponentially. Modern lumber treated with chemical preservatives might resist this process for 20 to 30 years, but Viking-age timber had no such protection. Oak, birch, and pine beams cut with iron axes and shaped by hand possessed only their natural defenses against moisture, dense heartwood, resin content, and grain orientation. Yet archaeological evidence reveals Norse timber structures that survived far longer than their modern equivalents. At the Stong farmstead in Iceland, stone foundation remains show a longhouse occupied for over 2 centuries, from roughly 1000 to 1200 CE. The timber walls are gone, dissolved into soil, but the raised stone sills remain exactly where Viking builders placed them 800 years ago. Dr. Einar Thorsen has excavated dozens of Norse building sites across Scandinavia and Iceland. His findings consistently show the same pattern. Structures built with direct ground contact leave only post-hole stains and scattered metal artifacts, while buildings constructed on stone foundations preserve clear sill beam impressions and substantial timber remains. At the Eiríksstaðir site in Iceland, we found oak sill beams still intact after 6 centuries, he notes, measuring a preserved timber fragment. The wood shows minimal decay because it never touched wet earth. The stone foundation created a 40-centimeter air gap that kept the timber dry. The typical Viking longhouse foundation system was elegantly simple. Builders selected flat field stones, often schist or granite slabs naturally split by frost, and arranged them in parallel lines marking the building's perimeter. These stones rose 30 to 50 centimeters above ground level, creating a platform for the timber sill beams that would support the entire wall structure. The sill beams, typically 15 to 20 centimeters thick and hewn from the straightest available timber, rested directly on these stone supports. Wall posts, either mortised into the sill or lashed to it with leather strips, carried the roof load down through the timber frame to the stone foundation and finally to solid earth below. This system solved multiple problems simultaneously. The raised foundation prevented moisture wicking from soil to timber, eliminated frost heaving that could shift wooden posts, and created airflow beneath the structure that carried away condensation and dampness. Even more importantly, it placed the most vulnerable part of the building, the connection between vertical wall posts and horizontal sill beams, well above the ground's destructive influence. To understand how dramatic this difference could be, we need to examine what happens when timber contacts earth in a cold, wet climate like medieval Scandinavia. I placed two identical oak samples in test conditions, one sitting directly on damp soil, the other elevated 30 centimeters above ground on a stone platform. After just 90 days of autumn weather, the results are stark. The ground contact timber shows moisture content of 22%, soft spots where fungal hyphae have begun breaking down cell walls, and dark staining from bacterial activity. The elevated sample measures only 12% moisture content, remains firm to the touch, and shows no signs of biological attack. The numbers tell a clear story, but the visual evidence is even more compelling. Under magnification, the ground contact timber reveals networks of fungal threads penetrating deep into the wood grain. These microscopic organisms secrete enzymes that literally digest the cellulose and lignin that give wood its strength. Within months, structural timber becomes spongy and weak. Within years, it fails completely. The elevated timber sample, by contrast, shows clean grain structure and intact cell walls, wood that could support a building for generations. Viking builders understood this principle through direct observation and bitter experience. A longhouse represented months of labor and scarce resources in a harsh environment where building materials had to be cut by hand, shaped with simple tools, and transported without mechanical assistance. The difference between a structure lasting 30 years versus 200 years meant the difference between prosperity and ruin for a Norse family. Stone foundations required more initial effort, quarrying suitable flat stones, moving them to the building site, leveling them carefully to support the timber frame, but this investment paid dividends across generations. Archaeological evidence from the Lofoten Islands in northern Norway reveals longhouse foundations built around 800 CE that supported occupied buildings until at least 1200 CE, a span of 4 centuries. The secret lies not just in keeping timber off wet ground, but in creating the precise conditions where wood naturally resists decay. Timber moisture content below 15% inhibits most fungi, while good air circulation prevents the stagnant conditions where bacteria thrive. Viking stone foundations achieved both goals through simple physics and careful craftsmanship. The contrast with modern building practice is striking. Today's typical house sits on a concrete foundation, but the transition from concrete to wood frame often creates thermal bridging and condensation problems that Viking builders avoided entirely. Our elevated stone platform, with its natural air gap and breathable interface, actually performs better in many ways then sealed modern systems that trap moisture and create hidden decay zones. When we measured thermal performance of our test foundations during a cold snap, the Viking-style raised stone platform maintained 3 degrees Celsius warmer temperatures at the timber interface compared to ground-level construction, simply because cold earth could not conduct heat directly from the wood. This temperature difference matters more than modern builders often realize. Each degree of temperature change affects wood's equilibrium moisture content, and warmer timber stays drier timber. The Vikings achieved this thermal advantage accidentally, as a byproduct of solving the moisture problem, but the result was timber that remained in the safe zone for decay resistance year-round. Even in the depths of Scandinavian winter, with temperatures dropping to -30°C, elevated timber stayed above the critical 15% moisture threshold where rot takes hold. Standing beside our test structures as autumn rain turns to winter sleet, the wisdom of this ancient solution becomes unmistakable. The timber sitting on stone remains solid and dry, while its ground contact twin darkens with moisture and shows early signs of the decay that will eventually reduce it to the crumbling remnant I held in my hands. The Vikings built for centuries, not decades, and their stone foundations made that durability possible, through understanding that still guides the best timber construction today. The pile of fieldstone beside our building site tells a 1,000-year-old story of patient Viking craftsmanship. Each flat slab has been selected for its ability to bear weight and shed water, just as Norse builders chose their foundation stones from stream beds and frost-split outcrops across medieval Scandinavia. Building a timber structure on raised stone foundations requires careful selection of materials and precise placement to create the stable platform that kept Viking houses dry for centuries. Olaf Gunnarsson, our master craftsman trained in experimental Norse archaeology, begins the foundation work for Structure A by excavating a shallow trench 30 centimeters wide and 15 centimeters deep along the planned building perimeter. The trench provides a level base and prevents the stone foundation from settling unevenly under the timber frame's weight. Each fieldstone slab, weighing between 20 and 40 kilograms, must be positioned with its flattest surface upward to provide solid bearing for the sill beams. Safety requires 2 people for lifting stones above 20 kilograms. One person should never attempt to move heavy foundation stones alone, as back injury from improper lifting technique can occur quickly when working bent over in trenches. The stones rise 40 centimeters above ground level, creating the critical air gap that separates timber from soil moisture. Archaeological measurements from the Stung site in Iceland show Viking foundations typically ranging from 30 to 60 centimeters in height, with 40 centimeters representing the most common elevation found at longhouse excavations. This height places the timber sill beam well above ground splash from rain, snowmelt, and seasonal flooding while remaining low enough for practical construction. Dr. Einar Thorsen notes that foundations exceeding 60 centimeters become unstable without mortar, while those below 30 centimeters provide insufficient moisture protection during heavy weather. The sill beams for both structures come from the same oak tree, ensuring identical wood properties for our comparison. Each beam measures 20 centimeters wide by 15 centimeters thick, dimensions that match Viking-age timber found preserved in Norwegian bog sites. Olaf shapes the beams using traditional hand tools, a broad axe for rough shaping, an adze for smoothing the bearing surfaces, and a draw knife for final finishing. The work proceeds slowly but precisely, each tool stroke guided by centuries of woodworking tradition passed down through experimental archaeology programs across Scandinavia. Structure A receives the full Viking treatment. The oak sill beam rests directly on the stone foundation with no gap or movement. Level placement requires careful shimming with flat stone chips, exactly as Viking builders would have adjusted their foundations to accommodate slight irregularities in the hand-hewn timber. The connection between stone and wood relies purely on gravity and friction, no nails, bolts, or modern fasteners that would create weak points for moisture penetration. This simple bearing connection has proven itself across centuries of Norse construction, from Iceland to Greenland. Wall posts mortised into the sill beam rise every 60 centimeters along the structure's length, supporting horizontal wall planks that complete the timber frame. The posts measure 15 centimeters square, substantial enough to carry roof loads, but not so large as to waste precious timber resources. Each mortise joint is cut by hand using chisel and mallet, creating the tight-fitting connections that give timber framing its legendary strength. Dr. Ingrid Bjornson explains that saga evidence describes Norse carpenters as highly skilled specialists whose precise joinery work was valued throughout medieval Scandinavia. Structure B presents a stark contrast. Identical in every dimension and using timber from the same source, this building sits directly on prepared earth with no stone foundation. The sill beam rests in a shallow depression cut into level ground, following the building practice that archaeological evidence suggests was used for temporary structures or by builders lacking access to suitable stone. This direct ground contact creates the conditions for moisture uptake and decay that our experiment is designed to measure. Both structures receive identical roofing systems to eliminate weather as a variable in our timber decay comparison. The roof consists of rough-sawn planks covered with modern roofing membrane, not historically accurate, but necessary to ensure that any moisture problems originate from ground contact rather than roof leaks. The buildings measure 3 meters long by 2.5 meters wide, large enough to house meaningful amounts of timber while remaining manageable for detailed monitoring. Instrumentation requires careful planning to capture accurate data without compromising the timber structure. Moisture sensors drilled into the sill beams at precisely marked locations measure wood moisture content at 15-minute intervals throughout the test period. The sensors, calibrated to accuracy within 1%, connect to data loggers that record measurements automatically regardless of weather conditions. Temperature sensors placed at the timber foundation interface monitor thermal conditions that affect moisture equilibrium and fungal growth rates. Additional monitoring equipment includes soil moisture probes placed adjacent to each structure's foundation to track groundwater conditions, and relative humidity sensors inside each building to measure interior air conditions. This comprehensive sensor network provides the quantitative data needed to document exactly how much protection the raised stone foundation offers compared to direct ground contact. The installation process requires drilling small holes in non-critical areas of the timber frame, then sealing around each sensor with clear silicone to prevent moisture infiltration that could skew results. Care must be taken to place sensors where they will not interfere with structural performance while still providing representative moisture readings from the most vulnerable areas of the timber frame. The sill beam represents the critical measurement point, since this horizontal timber bears the greatest moisture exposure risk. Calibration of all sensors takes place under controlled conditions before installation, ensuring that readings from Structure A and Structure B can be directly compared without concerns about instrument variation. The data logging system stores measurements in standard formats that allow analysis of long-term trends, as well as daily fluctuations related to weather conditions. Safety considerations during construction include proper lifting technique for stones and timber, eye protection when using hand tools, and secure footing when working on elevated surfaces. The stone foundation work requires particular attention since uneven stones can shift unexpectedly under load, and the hand tool work demands concentration to avoid cuts from sharp chisels and axes. Karen Liu, our safety coordinator, conducts briefings before each work session, and monitors for fatigue that can lead to accidents when using traditional building techniques. Weather protection during construction prevents moisture from affecting the timber before monitoring begins. Both structures receive temporary coverings during rain, and all cut surfaces are sealed immediately to prevent premature water absorption that could compromise baseline measurements. The goal is to begin monitoring with both structures at identical moisture content, allowing the foundation difference to emerge clearly in the data. As construction nears completion, the contrast between our two test buildings becomes visually striking. Structure A sits elevated and proud on its stone platform, the oak sill beam clearly separated from earth by 4 decades of airspace. Structure B hunkers close to the ground, its identical timber frame resting directly on soil that will soon begin its slow but relentless attack on the wood fibers above. The stage is set for winter weather to reveal which approach truly protects timber from the ancient enemy of ground moisture, exactly as Viking builders discovered through necessity over 1,000 years ago. The first frost arrives on a November morning that would have signaled the start of survival season for Viking families across Scandinavia. Ice crystals coat both test structures as our monitoring equipment begins recording the critical data that will prove whether raised stone foundations truly protect timber from winter's destructive cycle of moisture, freezing, and decay. The stone elevated structure A and ground contact structure B face identical weather conditions, but the numbers already emerging from our sensors tell dramatically different stories about timber survival. Within the first week of freezing temperatures, moisture readings reveal the fundamental difference between Viking foundation engineering and direct ground contact. Structure A, elevated on its 40-centimeter stone platform, maintains sill beam moisture content at 12%, well within the safe zone where fungal decay cannot establish itself. Structure B shows sill beam moisture climbing to 18% as groundwater wicks upward through capillary action, even as the soil surface appears frozen solid. Dr. Sarah Patel explains that frozen topsoil acts like a lid, trapping unfrozen moisture deeper in the earth that continues moving upward through microscopic channels in the wood grain. The thermal measurements prove equally revealing. Infrared camera readings taken during a -15 C cold snap show Structure A's sill beam maintaining -2 C, while Structure B's ground contact timber drops to -8 C. This 6-degree difference occurs because the stone foundation creates an insulating air gap that breaks the direct conductive path between frozen earth and timber frame. The elevated structure essentially floats above the ground's thermal mass, protected from the Earth's ability to drain heat from the wooden frame above. December brings the freeze-thaw cycles that medieval Scandinavians knew as the wood killer. Daytime temperatures rise just above freezing, melting surface snow and ice into liquid water that soaks into any available timber. Nighttime refreezing expands this water by 9%, creating internal pressure that splits wood fibers and opens new pathways for moisture penetration. Our ground contact structure B endures this cycle repeatedly as meltwater pools around its timber base, while structure A remains high and dry above the destructive freeze-thaw zone. By January, visual inspection confirms what the sensors have been recording. Structure B develops, the telltale dark staining at the base of wall posts where moisture has penetrated deep into the oak grain. A hand lens reveals the fuzzy white threads of fungal hyphae beginning their microscopic invasion of the wood cells. These nearly invisible organisms secrete enzymes that break down cellulose and lignin, literally digesting the timber from within. The process starts slowly, but accelerates exponentially once established, explaining why ground contact buildings often survive decades before sudden structural failure. Structure A shows none of these warning signs. The elevated sill beam remains its original golden oak color, with no darkening or soft spots indicating moisture problems. More importantly, core samples taken with a small drill bitted show clean, intact wood grain with no fungal penetration. The 40-centimeter elevation has created conditions where decay organisms simply cannot establish the foothold they need to begin breaking down the timber structure. The moisture differential becomes even more pronounced during late winter warm spells. When February temperatures climb above freezing for several days, ground contact structure B experiences what building scientists call a moisture spike, rapid absorption, as surrounding snow melts and saturates the soil around the timber base. Sensor readings jump to 24% moisture content, well into the range where aggressive wood rot fungi thrive. Structure A, protected by its stone elevation, shows only minimal moisture increase to 14% as it briefly absorbs humidity from the warming air. Wind-driven rain in March creates another test of the two foundation systems. Both structures face identical weather exposure, but Structure A sheds water cleanly off its elevated platform, while Structure B sits in pooled meltwater that cannot drain away from the ground contact timber. The stone foundation not only elevates the wood above standing water, but also provides natural drainage as runoff flows away between the foundation stones rather than collecting against the timber frame. However, the testing reveals one potential weakness in the Viking approach that requires attention. Strong winds can drive moisture horizontally under the elevated structure, and the air gap that protects against ground moisture can also channel windborne precipitation toward the timber if not properly managed. Archaeological evidence from Greenland Norse sites shows that builders often address this issue by placing flat stones or wooden planks as wind barriers between foundation stones, creating protected pockets of still air under the sill beams. Temperature logging throughout the winter documents another advantage of the raised stone system that Viking builders probably discovered through experience. The thermal mass of the stone foundation moderates temperature swings in the timber above, preventing the rapid heating and cooling cycles that stress wood fibers and create condensation problems. Days when air temperature swings 20 degrees from dawn to midday, Structure A's sill beam temperature changes only 8 degrees, while ground contact Structure B experiences the full temperature range as Earth conducts heat directly to and from the timber. The data becomes particularly compelling during a late winter ice storm that coats both structures in a thick layer of frozen precipitation. Structure B, with its timber base sitting at ground level, becomes encased in ice as freezing rain accumulates around the sill beam and wall posts. This ice shell creates perfect conditions for prolonged moisture exposure as the ice slowly melts over several days, maintaining timber moisture content above 20% for an extended period. Structure A, elevated above the ice accumulation zone, sheds its coating quickly and returns to safe moisture levels within hours. Bacterial activity measurements taken from wood samples in early spring show the cumulative effect of winter moisture exposure. Structure B harbors active populations of wood-degrading bacteria that have established themselves in the persistently damp timber, while Structure A shows negligible bacterial counts. These microscopic organisms work alongside fungi to break down wood structure, and their presence indicates that decay processes have taken permanent hold in the ground contact timber. By the end of our winter monitoring period, the quantified results demonstrate beyond question why Viking builders invested extra labor in stone foundations. Structure A maintained average moisture content of 13% throughout the cold season, while Structure B averaged 21%. A difference that translates directly to decades of additional service life. The temperature differential averaged 4 degrees Celsius in favor of the elevated structure, creating thermal conditions that further inhibit decay organisms. Visual inspection in April reveals damage that validates the sensor data. Structure B shows obvious weathering, with darkened timber, minor checking in the sill beam, and soft spots where fungal decay has begun breaking down wood fibers. Structure A remains structurally sound and visually unchanged, its elevated position having protected it from winter's assault, exactly as Viking foundations protected Norse longhouses through centuries of Scandinavian weather cycles that would have destroyed ground contact construction within decades. The thin sheets of birch bark in Olaf's weathered hands represent the missing piece of Viking foundation technology that archaeological evidence has only recently revealed. Vikings refined their stone foundation method by adding natural moisture barriers and elevated interior floors that created even better timber protection than our initial test demonstrated. By incorporating these historically documented improvements into Structure A, we can measure the full effectiveness of Norse building techniques that kept longhouses dry and structurally sound for centuries. Archaeological excavations at the Lonso Meadows site in Newfoundland uncovered fragments of birch bark positioned between stone foundations and timber sill beams, evidence that Viking builders understood the importance of breaking capillary moisture transfer even through stone contact. Dr. Einar Thorsen explains that birch bark, called björkskin in Old Norse, served multiple functions in Viking construction as roofing material, container waterproofing, and crucially, as a natural vapor barrier that prevented moisture from moving between different building materials. The bark's natural oils and dense fiber structure create an effective seal while remaining flexible enough to accommodate seasonal movement in timber frames. Installing the birch bark membrane requires careful preparation to match archaeological evidence from Norse sites. Each piece measures roughly 30 centimeters wide by 60 centimeters long, dimensions that correspond to bark sections that could be harvested from mature birch trees without killing the source. The bark strips overlap by 10 centimeters along their edges, creating continuous coverage across the entire stone foundation surface. Olaf positions each section with the bark's natural curve facing downward, allowing any moisture that penetrates the outer layer to drain away rather than pooling against the timber above. The installation process demonstrates why Viking builders valued this technique despite the extra labor involved. Birch bark must be soaked in water for several hours before installation to restore flexibility, then positioned while damp so it conforms perfectly to irregularities in the stone surface. Each piece requires careful smoothing to eliminate air pockets that could allow moisture penetration, and the overlapping joints need precise alignment to maintain the continuous barrier. Safety considerations include wearing gloves when handling bark edges, which can cause cuts, and ensuring secure footing when working on the elevated stone platform. Archaeological evidence from Iceland suggests that Vikings also elevated their interior floors above the sill beam level to create additional protection against moisture infiltration. At the stone farmstead, excavations revealed wooden floor planks positioned 10 to 15 centimeters above the stone foundation level, supported by cross joists mortised into the main sill beams. This elevated floor system created a double barrier against ground moisture, first the stone foundation and birch bark membrane, then an air gap beneath raised wooden flooring. Replicating this system in Structure A requires precision carpentry that matches the quality of medieval Norse craftsmanship. Floor joists measuring 8 centimeters by 12 centimeters span between the sill beams at 60 centimeter intervals, providing adequate support for plank flooring while maintaining the timber dimensions found at archaeological sites. The floor planks themselves, hewn from the same oak stock as our sill beams, measure 20 centimeters wide by 3 centimeters thick, substantial enough to carry floor loads but not so heavy as to overstress the supporting framework. The elevated floor installation reveals another advantage that Viking builders probably discovered through experience. The airspace beneath raised flooring creates natural ventilation that carries away any moisture that might penetrate the outer building envelope. This airflow prevents the stagnant conditions where decay fungi thrive, essentially creating a self-drying system that becomes more effective over time as temperature differentials drive air circulation through the floor cavity. Drainage improvements around the stone foundation address the potential weakness identified during our winter testing. Archaeological surveys at Norse farmstead sites consistently show evidence of deliberate drainage systems, shallow trenches filled with gravel or flat stones positioned to direct runoff away from building foundations. Following this pattern, we excavate a drainage channel 15 centimeters deep and 20 centimeters wide around Structure A's perimeter, sloping the bottom to carry water away from the foundation stones. The channel receives a base layer of coarse gravel topped with flat field stones, creating a permeable drain that handles both surface runoff and subsurface seepage. With these historically informed refinements in place, our monitoring equipment records dramatically improved performance from Structure A. Sill beam moisture content drops to 10% and remains stable even during spring's challenging conditions of snowmelt and frequent rain. The birch bark membrane creates an effective vapor barrier that prevents stone to timber moisture transfer, while the elevated floor eliminates the last pathway for ground moisture to reach the building's structural framework. Temperature measurements show additional benefits from the refined Viking system. The air gap beneath the elevated floor provides extra insulation that keeps interior temperatures more stable and reduces condensation risk. During a late spring warm spell that brings high humidity and temperature swings, Structure A maintains interior conditions that stay within the safe zone for timber preservation, while our control structure continues showing moisture problems that would lead to long-term decay. The cost analysis reveals why Vikings invested in these foundation refinements despite the additional labor requirements. Birch bark was readily available across most of Scandinavia and required no special tools or skills to harvest and install. The elevated flooring used the same timber and joinery techniques employed throughout Norse construction, adding perhaps 10% to total building time while extending structural life by centuries. For a culture where replacing a longhouse meant months of work and scarce resources, this represented an obvious economic advantage. Testing the refined system through another seasonal cycle confirms the cumulative benefits of complete Viking foundation technology. Structure A, now equipped with stone elevation, birch bark, moisture barrier, raised interior flooring, and proper drainage, maintains optimal timber conditions regardless of weather extremes. Moisture content never exceeds 11%. Temperature fluctuations stay within acceptable ranges, and visual inspection shows no signs of decay, checking, or other moisture-related damage that plagued ground contact construction. The contrast with modern building practice becomes even more striking when we compare total system performance. Our refined Viking foundation method outperforms many contemporary approaches to moisture control while using entirely local, renewable materials and hand tools. The stone and timber framework could be maintained and repaired indefinitely, while the birch bark membrane might require replacement every 20 to 30 years. Still a remarkable service life for a natural material protecting structural timber. Archaeological evidence supports these performance projections through documented building lifespans at excavated Norse sites. The Glaumberg farmstead in Iceland shows continuous occupation from the medieval period through the 19th century, with some foundation stones and structural timbers serving for over 600 years. The key to this extraordinary longevity lies not in any single technique, but in the integrated system that Vikings developed through generations of building experience in harsh northern climates. Our refined Structure A now represents the full sophistication of Viking foundation engineering: stone elevation for moisture protection, birch bark membrane for vapor control, raised flooring for interior protection, and drainage for water management. The monitoring data proves that this 1,000-year-old technology creates timber preservation conditions that modern science can measure but rarely improves upon, demonstrating once again that Viking survival methods succeeded through understanding principles that remain valid today. The final sensor readings tell a story that spans 1,000 years, connecting our modern measurements to the quiet wisdom of Norse builders who solved timber preservation through patient observation and practical engineering. Vikings kept their wooden houses from rotting by building them on raised stone foundations, and our year-long testing proves this ancient method delivers measurable protection that modern construction science can validate but rarely surpasses. The numbers document a clear verdict. Structure A, built with authentic Viking foundation techniques, maintained timber moisture content averaging 10% throughout all weather conditions, while Structure B, using direct ground contact, averaged 21% moisture, a difference that translates to centuries of additional service life. The temperature measurements reinforce this moisture advantage with equally compelling data. Our stone-elevated structure maintained sill beam temperatures averaging 4 degrees Celsius warmer than ground contact construction, creating thermal conditions that further inhibit decay organisms while reducing energy needed for interior heating. During the harshest winter conditions, when Structure B's timber dropped to -8 degrees Celsius, Structure A remained at -2 degrees, warm enough to prevent the freeze-thaw cycles that split wood fibers and create new pathways for moisture penetration. Visual inspection after 18 months of testing provides the most dramatic evidence of Viking foundation effectiveness. Structure B shows obvious signs of moisture damage, darkened timber, soft spots where fungal decay has begun, minor checking along grain lines, and the telltale white threads of wood-eating organisms establishing themselves in the oak fibers. Structure A remains structurally sound and visually unchanged, its golden oak color intact and wood grain showing no signs of biological attack. Core samples taken with precision drill bits reveal the internal story: clean, dense wood fibers in the elevated structure versus compromised cellular structure in the ground contact timber. Archaeological evidence supports these performance projections through documented building lifespans that extend our test results across centuries. The Eiríksstaðir reconstruction in Iceland, built using Viking foundation methods identical to our Structure A, has weathered 43 years of North Atlantic storms with minimal maintenance and no structural degradation. Original Norse buildings like the Stone Longhouse served families for over 200 years using these same techniques, while ground contact structures from the same period left only post-hole stains and scattered artifacts. Modern builders seeking to apply Viking foundation wisdom can implement 5 practical strategies that our testing proved effective. First, elevate timber sill plates at least 30 centimeters above ground level using flat stone or concrete pads, creating the air gap that breaks moisture transfer from soil to wood. This simple change reduces timber moisture content by an average of 8% based on our measurements, moving wood from the decay-prone zone above 15% moisture into the safe preservation range below 12%. Second, install a breathable moisture barrier between the foundation and timber using materials that block capillary water transfer while allowing vapor movement. Our birch bark membrane reduced sill beam moisture by an additional 2% compared to direct stone contact, and modern builders can achieve similar results using breathable synthetic membranes or traditional materials like cedar bark or heavy felt. The key is preventing direct contact between masonry and wood while maintaining airflow that carries away trapped moisture. Third, provide drainage around building foundations using the gravel trench method that archaeological surveys document at Norse farmstead sites. Our 15-centimeter deep drainage channel filled with coarse gravel eliminated standing water problems that affected Structure B, throughout the testing period. This simple improvement costs little, but provides permanent protection against seasonal flooding and snowmelt that can overwhelm even elevated foundations. Fourth, consider raising interior floors 4 to 10 centimeters above the sill beam level to create additional protection against moisture infiltration. Viking builders understood that this double barrier approach, stone foundation plus elevated flooring, creates airflow patterns that naturally dry any moisture that penetrates the outer building envelope. Our measurements show interior floor elevation reduces humidity levels by an average of 12% compared to floor systems sitting directly on foundation sills. Fifth, conduct annual inspections of foundation areas and timber moisture levels using simple tools that detect problems before structural damage occurs. Vikings maintained their buildings through regular maintenance schedules tied to seasonal cycles, replacing deteriorated elements before failure compromised the entire structure. Modern moisture meters costing less than $50 can provide the early warning system that extends timber building life from decades to generations. The economic advantages of Viking foundation methods become clear when we calculate long-term building costs. Structure A, with its stone foundation, birch bark membrane, and raised flooring, required approximately 15% more initial labor and materials than ground contact construction. However, the extended service life documented by archaeological evidence means the Viking approach costs roughly 1/3 as much per year of useful building life. For homesteaders, craftspeople, and anyone building in damp climates, this represents substantial savings over conventional construction that requires major repairs or replacement every 20 to 30 years. Jack Harrison, our homestead owner who observed the entire testing process, summarizes the practical impact with characteristic directness. I've seen 3 barns rot out in 25 years of farming, all built the modern way with treated lumber on concrete slabs. This Viking system makes sense. Keep the wood dry, keep it warm, keep it lasting. I'm building my next outbuilding on stone foundations 40 centimeters high, and I expect it to outlast me. The broader implications extend beyond individual building projects to questions of sustainability and resource stewardship that Vikings understood intuitively. Timber construction using local materials and human-powered tools creates structures that can be maintained indefinitely without industrial infrastructure. Stone foundations use materials that improve with age, developing better drainage and stability as frost action settles the masonry into permanent positions. The complete system represents appropriate technology that scales from single buildings to entire communities without depleting non-renewable resources or requiring specialized expertise. Standing beside our 2 test structures as autumn returns for the second year, the wisdom encoded in Viking foundation engineering becomes undeniable. Structure A continues weathering all conditions without deterioration. Its elevated position and carefully engineered moisture barriers creating the optimal environment for timber preservation. Structure B shows accelerating decay as fungal organisms establish permanent colonies in the moisture-compromised wood fibers. The ancient solution continues proving its worth through measurable performance that validates what Norse builders learned through necessity and perfected through generations of harsh climate construction. The stones that lifted Viking houses above the damp earth still teach us how to build for the long haul, one foundation at a time,